and then we'll start talking about life on Venus. So this is the impetus for this talk. It's not just a sudden interest in astrobiology on my part, but obviously there is a big news event, a big astronomical news event this past week. So big that some astronomers couldn't keep their mouths shut, and they broke the journalistic embargo on this story. In fact, astronomy Twitter, Sunday night, everyone was kind of whispering like, "Oh, there's something going to happen. Some news is going to come out." So we will talk about what that news is in a little bit. So first, I want to reintroduce you to Venus. So this talk is titled, "Is There Life on Venus?" AKA David Bowie was wrong. He asked the wrong question. So Venus is the second planet from the sun, typically the closest planet to Earth. It orbits the sun at a distance of about 7/10 of an astronomical unit. Remember, that's the average distance between the Earth and the sun. And it completes an orbit every 225 days, thereabouts. And it has the most circular orbit of all the planets. Here you can see Venus is the bright object right smack dab in the middle of the image, and it's even reflecting in the ocean there as well. That is the light from Venus. The bright dot towards the top of the image, that's Jupiter. Most planets orbit the sun in a counterclockwise direction. In fact, all of them do. And most planets rotate on their axes in that same direction. So the Earth rotates on its axis counterclockwise. Obviously, there's one big exception, Uranus. Uranus kind of rolls around, it tumbles as it orbits the sun. Venus is the other exception. Venus rotates clockwise every 243 days. So a day on Venus is longer than its year. Astronomers have some theories about that. The most prominent theory is that in its early history, in the early history of the solar system, Venus was just smacked with a huge object that caused it to physically flip over and slow down its rotation. So that's why its rotation is so slow and in the opposite direction. As for the exploration of Venus, that really started in 1962 when the Americans started sending the Mariner series towards the inner solar system. So Mariner 2, 5, and 10 were all flyby missions in 1962, 67, and 74. And then in quick succession, the Russians were really the ones who loved going to Venus. The Russians sent several landers and orbiters. So Venera 3 through 14 from 1966 to 1981. And then they sent the Vega missions in 1985. In fact, the image at the bottom of the screen is an image from Venera 9, where it's one of the few images we have taken from the surface of Venus. I sort of wish, I can't complain, it landed on another planet successfully, but I sort of wish the camera was tilted just a little bit further up. Those rocks look nice, but still. More orbiters have been sent by many more nations. So Venera 15 and 16 were sent in 1983 by the Russians. The Americans sent the satellite Magellan in 1990. The European Space Agency sent the Venus Express in 2006. And currently, there is one satellite orbiting Venus called Akatsuki. It's a Japanese satellite. But we really have not had anything land on Venus or go through its atmosphere since the mid-80s. That will be very important here in a little bit. The surface of Venus, very bad. Obviously, the surface is obscured by this constant cloud cover. That's the highly reflective thing that makes Venus so bright in the night sky. It's light reflecting off of the clouds. So the surface is only visible through those very few landers that have survived long enough on the surface and radar imaging from orbit, primarily through the Magellan spacecraft. Most of the surface is covered in what's called deposition plains, which are essentially plains made out of lava rocks. Ranges in elevation between 0 and 2 kilometers. It's a pretty flat planet. The rest is these highlands and lowlands. Compared to Mercury and the moon and other moons of the solar system, Ganymede, many of the moons of Jupiter and Saturn, Venus has very few craters. And that's pretty much because of Venus's thick atmosphere. You know, a lot of Earth is constantly bombarded by meteors, but they never reach it to the surface because they burn up in Earth's atmosphere. The Earth's atmosphere is fairly thin. Venus's atmosphere is much, much thicker than Earth, so hardly any meteors actually make it to the surface of Venus. They pretty much all burn up before they reach the surface. There are also, however, a few large meteors that do make it through, and those that do make it through, we can count how many craters there are on the surface. This is a very well-defined technique. It's actually called crater counting. It's how we determine the ages of the surfaces of these cratered worlds. And by counting craters, there's not many, like I said, and so this suggests this big theory to why there aren't as many beyond that. There are not many old craters. There are these tons and tons of young craters. The theory to explain that is that the entire surface of Venus goes through these periodic global resurfacing events. So Venus does not have tectonic plates like the Earth does. So all that pressure underneath the Earth's crust, all that magma builds up and is able to come out through volcanoes, through the cracks in the Earth's crust. But Venus does not have any tectonic plates. So this pressure builds up, and then every 300 to 500 million years, the entire planet essentially explodes, covering itself with lava, thus erasing any of these older craters, which is why we only see these craters that were created a very recent time ago. There are some volcanoes on Venus. They're not really that active. 80% of the surface is covered in those deposition plains, these lava plains, and they're dotted with these shield volcanoes. These are actually called pancake domes because these domes, which you see 3 of them here in this image, these are very wide, 65 kilometers, 40 miles wide, but they're only like a kilometer high because the magma just doesn't erupt. It's under so much pressure, it can't really spew out like it does on Earth. It erupts, and then it just slowly oozes out over these large expanses of area. And they number in the hundreds of thousands to millions. They're all over Venus. So the surface of Venus is truly dominated by this volcanism. Now we come to the atmosphere. So the atmosphere is the thing we know more about. I'm not going to say we know a lot about it, but we know more about it. The atmosphere is mostly carbon dioxide, 96.5% carbon dioxide, 3.5% nitrogen with traces of other gases. But those gases aren't fun gases. We're talking things like hydrochloric acid, hydrofluoric acid, carbon monoxide, sulfuric acid, hydrogen sulfide, and then phosphorus and phosphoric acid. So you definitely do not want to step out of your spaceship on Venus. The lowest part of the atmosphere, the troposphere, is the densest. The atmospheric pressure on the surface of Venus is 92 times that than on the surface of Earth. It is as if you were 9,000 meters below the ocean surface. That's how much atmospheric pressure is. In fact, it's so dense that carbon dioxide doesn't really exist as a gas on the surface of Venus. It exists as this weird supercritical fluid, sort of like a fog here on Earth. The large amounts of this CO2, together with the smaller amounts of water vapor and sulfur dioxide, create a strong greenhouse effect. In fact, Carl Sagan was the one who first proposed that the Earth could experience a similar greenhouse effect because he studied Venus. This greenhouse effect makes Venus the hottest planet in the solar system, has a surface temperature of about almost 900 degrees Fahrenheit, which is hotter than Mercury, even though Mercury is way closer to the sun. The winds can be turbulent and they can be mild. So high in the clouds, the wind speeds are at 100 meters per second, or about 224 miles per hour. But at the surface, they're only about a meter per second, or about 2.2 miles per hour. That sounds low, but because of the density of the atmosphere and the high pressures, that's still a strong wind. It's still able to push pebbles along on the ground. So it's still very impressive for Venus. Here's a little diagram of the different layers in Venus's atmosphere. So we've got altitude in kilometers on the left vertical axis, temperature in degrees Celsius on the right vertical axis, and then detached from the figure is pressure in bars on the right vertical axis. So you see at the surface, obviously that's where all the rocks are, but there's also this kind of surface haze. We might call it fog here on Earth, but fog on Earth is temporary. I mean, it's there in the morning, and then by the time the sun warms up the air, it's gone. This haze is there pretty much permanently. It's not clouds, it's just this kind of haze. Then as we go higher up into the clouds, probably about 40 to 60 kilometers, we get into this cloud deck. What the interesting thing about it is this high up, the temperatures, if you look at the right vertical axis, the temperature is about 60 degrees Celsius. It's a pretty temperate kind of place. This is where life could be. We'll talk a little bit more about that in a little bit. And it's at the right kind of pressure. It's only about 1 bar, which is the pressure at the Earth's surface. And of course, as you go further up, you start getting into the less dense air to the where we're starting to hit the edge of space, and the temperature just plummets. All right. So that's kind of your overview of Venus. But now let's talk about how can we measure things about atmospheres. So deep in the atmosphere, once again, here on the vertical axis is the pressure in bars. A third of the way on the horizontal is the temperature in Kelvin. We won't really worry about that part. But how do we measure things in the atmosphere? So deep in the atmosphere, the pressure and temperature are such that thermodynamical equilibrium and radiative convection equilibrium prevail. In other words, chemical reactions will occur faster than kinetic ones. So there'll be a lot of chemistry happening here near the surface. Higher up, we've got various processes that are more prevalent, including atmospheric circulation, vertical mixing, clouds, hazes, thermal inversions. These will influence the composition and temperature of this kind of middle layer of an atmosphere. Further up, you get into this low density but high solar radiation. Lots of light are happening here, so you cause photochemical processes to govern the composition. So light will break apart molecules, and they'll also provide energy to molecules to do these chemical reactions. It's called photochemistry. And then even at the highest altitudes, at the lowest pressures, this is when you are kind of at the edge of space for this planet. And at that point, molecules can easily escape the atmosphere, and it leads to mass loss of an atmosphere for a planet. So UV observations will probe the uppermost regions of an atmosphere. There you'll see things like ionized hydrogen, some organic compounds, magnesium iodine, some silicon. That's what you see in the upper atmosphere. The infrared observations will probe deeper into the atmosphere, where we're looking at molecules like water, carbon monoxide, methane, hydrogen cyanide, carbon dioxide, and ammonia. And then optical observations will probe in between. So looking at things like sodium atoms, potassium atoms, titanium oxide, vanadium oxide, stuff like that. So depending on what part of the atmosphere you are scientifically interested in, that will determine what kind of observation you will do. So now let's talk a little bit about biosignatures. I'm kind of jumping all over the place, but this is all stuff you kind of need to know. This is less of an astronomy talk and more of a here's a chemistry and biology talk. So a biosignature is some gas that fulfills these criteria. One, it does not have any false positives. It can't be mistaken for any other element or compound. Two, it has strong enough spectral features to be detectable. Obviously, we need to be able to see it. And three, it's abundant enough to be detectable. Once again, there needs to be enough of it for us to see it. So traditional biosignatures based on the Earth's atmosphere have been long thought to be molecular oxygen, O2. We also have ozone, nitrous oxide, and methane. However, as astrobiologists and exoplanetary scientists continue to think about this, there may not be a single ideal molecule that will scream, look, there's life on this planet. But instead, there may be this combination of multiple types of molecules that may be a potential biosignature. And so we need to be open to surprises. As is the case in science, nature has rarely conformed to our expectations. There may be a non-denumerably infinite number of possible biosignatures. So things like carbon dioxide, methanethiol, methyl chloride, ethane, ammonia. Oops, there we go. The list goes on and on. In fact, oxygen, nowadays, we know it can be produced geologically. So even if we find oxygen on a planet, that's not necessarily an indication of life. If there's a bunch of different biosignatures, then that will be more likely an indication of life. So all that to say, it's not like we're going to have this binary yes or no, there is life. We'll have more likely a probability spectrum where we'll say, 75% chance there's life on this planet. So now that I've brought you up to speed on what you need to know about Venus and how we look at atmospheres and what biosignatures are, now let's dig in to the nitty-gritty of this Venus news story. So Jane Greaves, she's a professor and researcher at Cardiff University in the United Kingdom. She and her collaborators have the goal of just providing a benchmark for future studies. They were not looking for anything. They were just trying to, here's a benchmark. But instead, they did find something interesting, as we all know. So they used the James Clerk Maxwell telescope to take the spectrum of the atmosphere of Venus in June 2017. So what is that James Clerk Maxwell telescope? The JCMT, which those initials together make it sound like it's a boy band member. The JCMT is a telescope located on Mauna Kea in Hawaii. It was built in 1983 and it was first started operating in 1987. It is the big cylindrical building here in the middle of the image. That's the JCMT. It was originally owned by the UK, Canada, and the Netherlands, but ownerships have changed over the years and is currently owned by Japan, China, Taiwan, and South Korea. And it's named after the Scottish physicist James Clerk Maxwell, who formulated the theory of electromagnetic radiation. It is a submillimeter telescope. So it is not an optical telescope. It does not look at optical light, the light that we see with our own eyes. It looks at light with wavelengths between a few hundred micrometers and a millimeter. So don't think, when you think sub-millimeter telescope, do not think typical optical telescope. This is the Warner and Swasey telescope here at Case Western. It's a 9.5-inch refractor. I took this image, and in fact, I think it's actually pointed at Venus, which maybe you can see. I don't know, Zoom sometimes does things with images, but Venus is there in the image. So when you hear sub-millimeter, all the telescopes we'll talk about tonight are not these optical tubes you're familiar with. In fact, they probably look more like this. This is a C-band satellite dish in my grandparents' yard. This is the kind of telescope we're talking about. As we get to these longer wavelengths, these tube refractor and reflector telescopes aren't going to do us any good. We need these kind of radar dishes, if you will, to see this kind of light. So this was the initial detection. They looked at Venus with the JCMT, and they found this absorption feature at the wavelength of phosphine, which is about just over a millimeter. So I pointed it out there in this figure from their paper. that dip in this spectrum, there's random noise to the sides, that dip is phosphine. So orange, their orange dotted line is the most conservative fitting technique. The black solid line is the least conservative fitting technique. Regardless of what technique they use, there is definitely a dip there in the spectrum of Venus. But the signal is kind of weak. JCMT is a great telescope, but it's not the best telescope for this purpose. And you could really confuse this with a data artifact. This could be just random noise or another molecule that absorbs at a nearby wavelength. So they had to follow up this detection. So they, with this signal, they were able to get time on the Atacama Large Millimeter Submillimeter Array, also known as ALMA. It is located in the Atacama Desert in Chile, built in 2008, first operated in 2013. It was owned by a multinational partnership between Europe, the US, Canada, Japan, South Korea, Taiwan, and Chile. It cost about $1.4 billion, so it is currently the most expensive ground-based telescope in operation in the world. In fact, it was so difficult to build, they had to, similar to how during the Apollo missions, they transported the Saturn V rocket from the vehicle assembly building to the launch pad on top of this crawler transporter, this massive just platform that moved on treadmills at like 1 mile per hour. They had to build another one of those to move the 50 12-meter essentially radio dishes, antennae, up the mountains. But because there's 50 of them, this gives it more resolving power than JCMT. ALMA is a much, much better telescope for this kind of thing. So they looked at Venus with ALMA, and they confirmed the detection. This is the data from ALMA. Once again, you see random noise on either side of this absorption trough at the wavelength of phosphine. For this, if these two things were not related, if this wasn't phosphine, for this degree of coincidence, any contaminating molecule that wasn't phosphine would have to have a wavelength that's the same as phosphine within 10 to the minus 6. So is probably phosphine. But we're scientists. We need to be careful about making any concrete statements. So now we've got a test. Is this actually phosphine? Could other gases in Venus's atmosphere absorb at nearby wavelengths? Well, they checked these large tables of elements and molecules and their absorption features that we've studied in the lab here on Earth, so we know at what wavelength, at what frequency they will absorb light at. And the only thing that was in Venus's atmosphere that could be near phosphine is sulfur dioxide. One of its transitions will produce a similar feature. So let's look at it. Here is their data again. So the dark black, the bolded black part of this line is where sulfur dioxide should be. There's not really anything there. The dotted red line is what sulfur dioxide at 10 parts per billion would look like. And then the solid red line is the strength sulfur dioxide would have to look like phosphine. Clearly, sulfur dioxide there's not enough of it there at that transition to mimic this signature. So there's no reason to believe that this detection was not phosphine. And as far as I can tell, I've read the paper, other radio astronomers have read the paper. I'm not a radio astronomer, but other astronomers who are radio astronomers have read the paper, and no one has really come up with any reason to believe that this signal was not phosphine. So, where is the phosphine? So the absorption width of these spectra are characteristic of signals from the upper atmosphere of Venus. The continuum they measure, the random noise that's on each side of this absorption signal, it comes from clouds that are around 53 to 61 kilometers up. So the phosphine must be at least this high up. That puts it, if you see, I've marked it with these red dashed lines in that figure, that puts it kind of smack dab in the middle of that temperate zone where It's at the right pressures and temperatures for it to be relatively pleasant if it wasn't, for all the acid in there. Phosphine is also detected most strongly at the mid-latitudes between the equator and the poles of Venus, and not detected at the poles. Although they didn't elaborate further on, they needed more data to talk about specifics. And then abundance modeling for phosphine gives it an abundance of 20 parts per billion. So it's not a lot of phosphine. It's not like we found, huge chunks of rock that are made purely of phosphine. We found a few molecules of phosphine, 20 parts per billion. All right, what is this phosphine I keep mentioning? So phosphine, chemical abbreviation PH3, it's one phosphorus atom with 3 hydrogen atoms bonded to it. It is a colorless, flammable, very toxic gas. It easily burns with oxygen to create phosphoric acid, and then phosphoric acid is then subsequently found in soaps, detergents, and toothpaste in low amounts. So if you're one of those people who are worried about the chemicals you're putting in your body, you do not have to worry about the phosphoric acid in your toothpaste. It is fine, I promise you. We have found it in 3 other places in the solar system. The 2 big places are also 2 big places, Jupiter and Saturn, found deep in their atmospheres, where there the pressures, temperatures, and concentrations of molecular hydrogen, that is 2 hydrogen atoms bound together, are high enough for the formation of phosphine to be chemically favored. It forms phosphine naturally, it just happens. We've also found it here on Earth. Phosphine is found in Earth's atmosphere almost exclusively as a byproduct of microbial activity and human industrial activity. So, but very, very small amounts. Here we're not talking parts per billion levels, we're talking parts per quadrillion or parts per trillion levels. Very small amounts of it in our atmosphere. But that is why phosphine is a biosignature, because as far as we know on Earth, it's only produced through biology. Sadly, we only understand its chemistry as a means to do industrial things with pharmaceutical. We know pharmaceutical reactions, we know agricultural, industrial reactions, but as far as biological reactions, we have very little information. Furthermore, Venus, like I said, we haven't sent something through Venus's atmosphere since the 80s. So we know some things about Venus's atmosphere, but not enough. This is really a comedy of errors where they weren't looking for phosphine and then they happened to find it and they found, the molecule that we know not a lot about in the atmosphere, we know not a lot about. So it's really just this whole comedy of errors. But we will march forward and see what we can say about this. So let's look at how fast should phosphine be produced for us to measure 20 parts per billion concentration in Venus's atmosphere. So the abundance of phosphine on Venus is a result of the balance between its production and destruction. Makes sense. So let's see if we can model how it's going to be destroyed, and then we'll worry about the production. So broadly speaking, I'll try not to get into the nitty-gritty, but in the upper atmosphere of Venus, attacked by oxygen, which sounds like the title of a horrible science fiction movie, is the main loss mechanism. In oxygenated environments, such as the Earth's atmosphere, such as Venus's atmosphere, the hydrogen bonding to other things is not favored over oxygen bonding to it. Oxygen really wants to bond onto things. So what would be favored is oxygen will take the place of the hydrogen and it will instead form phosphoric acid. So that's how it will be destroyed in the upper atmosphere. In the mid-atmosphere, here we're talking about attack by chlorine. So chlorine really wants a partner. And if there's phosphorus around, then it will readily bond to phosphorus and form chlorophosphate. So that's how phosphine could be destroyed. In the deep atmosphere, the temperatures and pressures are so high in the deep atmosphere near the surface that just the temperature alone will break up phosphine. The molecular bonds are not strong enough to hold it together at those high temperatures. So that's what you see here on the right in this figure. So the vertical axis is the altitude in kilometers. The horizontal axis is the lifetime of phosphine in seconds. So in the deep atmosphere, in the mid-atmosphere even, up to about 60 kilometers, the lifetime of a phosphine molecule, we're talking about maybe 3 centuries. Up in the upper atmosphere, the lifetime of phosphine, we're talking about a fraction of a second. So it's really not going to survive in the upper atmosphere. So this phosphine must be coming from the middle layers of the atmosphere. Given all these possible destruction mechanisms, to balance those destruction mechanisms, Venus has got to be producing phosphine across the surface of Venus at a rate between 8,000 to 80,000 tons per year. So now that we know how fast it needs to be produced, let's look for these mechanisms that could be producing phosphine. So production mechanism 1 is photochemical synthesis. These are chemical reactions that are caused by the energy from sunlight. Could this cause phosphine to be created? Maybe. Well, this graph kind of shows it all. So on the vertical axis, we have the reaction rate. We don't care about the units. Don't worry about it. The horizontal axis is the altitude in kilometers. The red line is the destruction rate that we just talked about. The blue line is the forward reaction rate. How many reactions are going to proceed? At no point does the blue line go above the red line. That's bad. That means that phosphine is being destroyed faster than it's being produced. If all of it was going to be produced by photochemistry. In fact, even though we don't know a lot about the chemical reactions that will produce phosphine biologically, we can sort of take a stab at it. So this is a chemical reaction chain that could create phosphine. Phosphine is on the far right, the pH 3. And the different colored arrows and dashed lines represent the rate, the forward reaction rate divided by the destruction rate, where green means that things are going to happen fast. We don't have to worry about that reaction. This dark brown maroon color, things are going to happen very slowly. And I've circled here in red one particular compound called phosphorus monoxide. It's just one phosphorus atom and an oxygen atom. That is the bottleneck of this whole thing. Every reaction goes through phosphorus monoxide. And almost every single arrow leading away from phosphorus monoxide is a slow one, where it is not at all favored to proceed to a different route. For example, one of the reactions, phosphorus monoxide goes to a phosphorus atom and a hydrogen atom combined. There's no reason for hydrogen to swoop in and take the place of oxygen, especially in the oxygenated environment that is Venus's atmosphere. So this is really the bottleneck. The fact that we can't get away from phosphorus monoxide is really spelling doom for this photochemical method. In fact, the maximum predicted rate from these processes is more than 10,000 times lower than to match those observations of 20 parts per billion. So photochemical synthesis is not the way. But maybe it's thermodynamics. Maybe if the energy is favorable, reactions will happen spontaneously. We don't have to worry about energy from the sun. Maybe under certain conditions, temperatures, pressures, concentrations, spontaneous reactions will occur. So in the atmosphere, the conditions, like I keep saying, really favor oxidized phosphorus compounds. So at high altitudes, phosphoric acid dominates. At low altitudes, tetraphosphorus hexoxide dominates. I hope you all remember your organic chemistry nomenclature. Creating phosphine from these chemicals is too energetically costly. Like I keep saying, hydrogen is not going to readily take the place of oxygen, and oxygen certainly is not going to readily give up its spot to phosphorus. So that's in the atmosphere. On the surface, obviously it's rocks, and rocks are typically made out of iron compounds, but none of the iron compounds that we know about can really change these atmospheric chemicals into phosphine. Underneath the surface, who knows? We actually know very little about what the subsurface of Venus is made out of, if it has a mantle, what's the core is made out of. None of the landers that we sent back in the 60s, 70s, and 80s told us any of that information. They were designed to tell us that information. So we have no idea what could be happening underneath the surface. This weirdly colored plot is hard to explain. On the vertical axis is the altitude in kilometers. The color coding is number of reactions. So the yellow is 0 reactions. The dark blue is 15,000 reactions. Along the horizontal is something called the Gibbs free energy. You don't need to really, if you don't remember that from your chemistry classes, don't worry about it. All you need to know is that for a reaction to proceed spontaneously, it needs to have negative Gibbs free energy. So that means on the left side of this diagram, that's where the negative numbers are on the horizontal axis. And you look up and you see all the colors, and they're all this pale yellow. There are 0 reactions that have negative free energy. Therefore, there really aren't any way for spontaneous reactions to occur. They're just not energetically favored. Maybe mineral phosphides could form in the mantle of Venus and survive volcanic eruption to be converted into phosphine in the atmosphere. For this, we have to look at Earth. We can look at the ground in Earth, look at the subsurface mineral content, and phosphides are fairly rare on Earth. And based on the rarity of them on Earth, at least 300,000 tons would need to be erupted from the mantle of Venus every year and then be 100% converted to reproduce the observed abundance of phosphine. This is equivalent to the most active volcanic eruption on Earth in the last 500 years, happening every year on Venus. That doesn't happen. The image on the back of the slide is called the Deccan Traps in India. It is the result of that most active volcanic eruption. That eruption was a pretty constant eruption for about 250 million years. So it's a really big deal. That is not happening on Venus. So once again, thermodynamics is not the way to produce phosphine. The people who wrote this paper did a very good job of going through all the other crazy ways we could produce phosphine. So maybe meteorites could deliver phosphides to Venus. Well, the Earth is being constantly bombarded by meteors. It actually accretes meteors at a rate of between 20,000 to 70,000 tons per year. The Earth's mass is growing. Of those meteorites, only the iron-nickel meteorites carry these phosphides, and only 6% of those meteorites that hit Earth are these iron-nickel meteorites. And of those iron-nickel meteorites, they only contain 0.25% phosphorus by weight. So if you run the numbers, assuming that Venus is just being bombarded, even that is still 100 million times too low to produce the observed abundances that we got. So thermodynamics is not it. Let's look at some weirder things. Maybe lightning. Remember, this reaction is not energetically favorable. So maybe if randomly some energy is imparted to these compounds, will phosphine proceed? Lightning is a great imparter of energy. But even if the products of Venusian lightning accumulated over one Venusian year with no destruction, it would still only measure to 3/4 of a part per quadrillion, which is 10 million times lower than the observed value. So lightning is not producing all this phosphine. Maybe Venus quakes. So there are some reactions that rely on mechanical energy to start the reactions. Quartz is one of those rocks that is able to do this. But even if all the energy from Venus quakes was used to convert phosphate to phosphine in rocks, it's still 100 times too low. And once again, Venus doesn't really have any tectonic plates. So where are the Venus quakes coming from? So that's not a great mechanism. What about an asteroid impact? So a very large asteroid impact slamming into the surface of Venus could impart some energy and produce phosphine. But even that meteor that killed the dinosaurs, the Chicxulub meteor, it didn't change the chemical nature of the atmosphere. We didn't suddenly go from an oxygen atmosphere to a methane one or something like that. So it didn't change the Earth's atmosphere drastically. So it would need to be a bigger meteor than the one that killed the dinosaurs. And there's no evidence of that, of a larger impact on Venus. The craters aren't that big on Venus. The final production mechanism that the authors of this paper could come up with is, it is possible that maybe there's some weird exotic chemistry happening on Venus that hasn't been considered. Like I said, we don't know a lot about the biological reactions of phosphine. So maybe there is just some chemistry that we just don't know about that's happening on Venus. But the authors say that just replaces the implausibility of making phosphine with another equally implausible set of conditions to make phosphine. So it's probably not this weird exotic chemistry. So we return to the original question then. Is there life on Venus? We have exhausted a lot of abiotic reactions to produce phosphine. So we've run out of abiotic reactions. Maybe life is actually producing phosphine. So maybe we need to explore that. Wow, that's my bad animations there. So if life exists on Venus, there's a lot of challenges that it will have to overcome. So first of all, life will have to exist inside liquid droplets in the clouds. A free-floating cell will just lose water until it matches the environmental concentration. On Venus, the atmosphere is at least 10 times drier than the driest places on Earth. So these cells, these microbes, have got to live inside liquid droplets. They've got to have also some way of surviving these sulfuric acid clouds. Now, some people point towards extremophiles here on Earth. These are microbes that are living in extreme conditions that thrive in them. We have examples of these terrestrial polyextremophiles that can tolerate very low pHs, very acidic environments, high temperatures, low water environments with a quote unquote high concentration of sulfuric acid. And so many researchers have taken that to imply that Venus life is likely. But I cannot stress enough how incorrect that is. The most acidic place on Earth is the Dalal geothermal area in Ethiopia. It has acidic pools of water that are at 108 degrees Celsius, so above boiling. They are hypersaline, full of salt, and they have anoxic hydrothermal sites containing about 150 grams per liter of iron, so they're not great. And they have the lowest pH recorded to date on the surface of the Earth. The pH scale goes from 0 at very acidic to 12 at very basic. So 12 is like, or I think 14, sorry. 14 is bleach. It's higher, that's higher than bleach, but bleach is a very basic thing. The Dalal geothermal area has pH of negative 1.7. Here on Earth, when we talk about sulfuric acid, hopefully you don't play with it in chemistry class, but when you do experiments with it in chemistry class, what you're doing experiments with is water with sulfuric acid dissolved in the water. Venusian clouds have sulfuric acid with water dissolved in it. In fact, the acidity of the Venusian clouds actually breaks the pH scale. It can't go that negative. So they had to invent a whole different scale called the Hammett scale, I believe. So the Venusian clouds are 100 billion times more acidic than the most acidic place on Earth. Whatever life is existing in those clouds has to have found some way to deal with that. The cells will also have to have some special mechanism for water absorption and retention. The Venusian atmosphere is equivalent to 7/100ths of a humidity at room temperature. The driest air on Earth in Death Valley has 2% humidity. So this is drier than the driest place on Earth. Life has to get all of its nutrients from the aerial biosphere. The Earth has microbes that live in the air, but their life cycle relies on the fact that at some point they'll be deposited right back on the habitable surface. So they don't have to live very long in the atmosphere. The surface of Venus is not habitable in any sense of the word. So whatever life exists in these clouds has to stay in the clouds. And so therefore they have to get all of their nutrients from the clouds. Venus, Venus's atmosphere is very scarce in hydrogen. So these biochemically critical molecules like methane and ammonia will be costly to produce. And metals are scarce in an atmosphere, and that will be a major growth limiting factor. And then life will have to be photosynthetic to survive because there's little chemical energy potential in the atmosphere to get energy from. So let's zoom through my crab animations there. And let's rebuild them. This is one proposed life cycle for microbes living in the clouds of Venus. So once again, on the left vertical axis is altitude in kilometers. The dashed lines indicate that we're talking about in the temperate zone. The left right vertical axis is the temperature in degrees Celsius, and the right vertical axis is the pressure in bars. So this is one proposed life cycle for life in the clouds of Venus. So I'll walk you through these 5 steps. So step 1, desiccated spores will persist in the lower haze. This lower haze is an altitude of about 20.5 to 29.5 miles up, temperatures between 170 and 370 degrees Fahrenheit. Then updraft will move these spores up into the habitable layer. That's step 2. Step 3, the spores will accumulate liquid in the clouds and germinate and become metabolically active. Step 4, these metabolically active microbes will grow and divide within the liquid droplets, while the droplets will grow by coagulation, just like rain does here on Earth. And then step 5, the droplets will rain out of the atmosphere. But as these droplets start to fall, the temperature will increase, and hopefully the high temperatures and the evaporations will trigger cell division and sporulation. They'll become spores. And once they're spores, they are small enough to actually stop falling out of the atmosphere. So they won't reach, so very few of them will reach the surface and be killed by the high temperatures and pressures. That's one hypothesized life cycle for life in the clouds on Venus. There have been many others. That's just one hypothesized one. Recently, using a very, very hand-wavy argument, and they admit that. They write in their paper that it's very hand-wavy. We don't have all the information. Lingham and Loeb suggest that the Venusian clouds could contain 40,000 tons of biomass at a density of 0.0001 milligrams per cubic meter. So for comparison, Earth's total aerial biomass is about 1 trillion tons at a density of 44 milligrams per cubic meter. So not that much, all that to say, not that much life, if it exists, will be in the clouds in Venus. Very small amount. So, is there life on Venus? Only time will tell. I will say that the problem with scientific news articles is that they hear life and then that's what they grab onto. If you read these papers, every scientist as part of these papers, and every scientist who's not a part of these papers, is extremely hesitant to say we have found life. There are certainly things we do not know. They are all saying we need to do more follow-ups from the ground with other telescopes, using other setups to see if we can reproduce this phosphine detection. We certainly need to go back to Venus. America hasn't been to Venus since the 1990s, and there are a few missions being proposed to NASA at the moment. Before all this happened, they were already being proposed to send NASA back to Venus. There's currently a Russian mission that they are working on called Venera D that will land on Venus, giving us more information about the clouds and the surface. So all this to say, is there life on Venus? Maybe. We just do not know at this point. So thank you very much. I will stop the share and then we will stop the recording.